Okay, good afternoon, everyone. My name is Changlong Wu. I'm from Vector, and today I'm going to share with you about our insight of Rust in AutoSAR. And now let's look at the motivation at first. Now let's think about a question at first. Why is the automotive software development so difficult, or let's say much more complicated than we thought at the beginning? Because automotive software is a unique combination of so many different complex requirements from different aspects. First, the automotive system must meet very high safety requirements, just as aircraft and trains and industrial automations. But second, the automotive industry is a high volume production industry. High volume production means that even you have a defect with very, very low chance, if you multiply it with millions of vehicles per year, it will definitely happen. And high volume production means high cost pressure. If you even increase just $1 cost per vehicle, it will sum up with a huge number in total. And third, the automotive industry, the automotive system is a distributed system. You may have many subsystems that are developed by different teams and even from different suppliers. And they must be assembled together and work together at the end. And the management of a distributed development is much more complicated than a centralized system. And fourth, since the vehicle is a physical system that moves at high speed, the control system of automotive system must meet very hard real-time requirements. And last but not least, the automotive industry is a highly regulated market. If you want to put a vehicle model into the market, you must meet dozens of regulations. And in different countries, these regulations may be different. So the automotive industry is a combination of so much different complex requirements. So we are facing contradictory requirements in software development. Like on one hand, we must speed up our development. We must put more functionality in shorter time. But on the other hand, we must, the quality requirement for the automotive software is also increasing. So how can we solve this problem? One solution is software standardization, just like AutoSAR. AutoSAR is the best practice of automotive software standardization, as you are already familiar with. But today, I'm going to introduce a new technology, Rust. Rust is a modern programming language that are developed based on lots of good and bad experience with other languages. The goal of Rust is to empower everyone to build reliable and efficient software. You may ask, there are so many modern programming languages. Why do we choose Rust? First, Rust is a high-performance programming language. Rust has very good optimization for the memory usage, and you don't even need to care about the garbage collector at runtime. There are also performance testing reports showing that the performance of Rust is just slightly worse than C language, and it's very close to C++. This makes it very suitable for the applications in automotive embedded system, because we usually have very limited hardware resources in our controllers. And second, the Rust is well known for its high reliability. Rust has introduced many new mechanisms like the type system and the ownership model that can guarantee the memory safety and thread safety at compile time. So you can avoid many of the bugs, the common issues at compile time, even before it runs. There are also saying in the Rust community that if a Rust program compiles, it can already work. Third, the Rust programming language has high productivity. The Rust has great comprehensive documentation, and the compiler of Rust is very powerful. It can give very useful, very detailed error messages and hints. You can fix the problem easily just by following the hints of the compiler. There are even jokes about the Rust programming, that Rust is a compiler-oriented programming language. And Rust has also mature tooling, which I will tell more about in detail later. And this tooling can help us improve the software development efficiency and improve also the quality. So because of all these advantages of Rust, Rust is becoming more and more popular. The TOB index ranks the popularity of different programming languages, and now Rust is on position 13. It has just moved up by one position than last year. And in the developer survey of Stack Overflow, Rust has become the most admired programming language in the last 10 years. And you can see the leading position of Rust is far ahead than other languages. And because of the high performance and high reliability of Rust, Rust has already been applied in many different areas. Like in internet area, the cloud server provider like AWS and Microsoft Azure start to provide services in Rust. And the web provider like Meta and Cloudflare are already using Rust to improve their product efficiency and performance and reliability. Then in operating system area, Microsoft has begun to rewrite some Windows kernel codes with Rust. And Linux also accepts now Rust as the development language for the kernel. And the mobile operating system like Harmony OS and Android now also support Rust as a development language for applications. Now let's look at the automotive industry. The application of Rust is rather in an early stage. According to public information, only Volvo and Ampere, that's the EV brand of Renault, are using Rust for their production software development of their vehicles. Okay, so much about the background. Now let's take a look at the technical opportunities and challenges with Rust. Why do we think Rust is the future for automotive industry software? First, Rust has introduced many new mechanisms to ensure the memory safety and thread safety. Like type system, we know that in CNC++, the null value and null pointer is a common issue at runtime. But with the type system of Rust, you can avoid this problem already at compile time. And another key feature of Rust is the ownership model and the borrow checker. Rust introduces very strict rules for the memory management. You don't need to manage the garbage collector at compile time, just as CNC++. So you can avoid the common issues like dangling pointer or double free errors. And we know that today in CNC++, one of the biggest issue is race conditions. We have semantic analysis, we have functionality test, but race conditions is still untestable today. And But if with Rust, we can guarantee the memory safety at compile time so that we can get rid of this problem completely. And because of the strict checking rules of the Rust compiler, we can reduce the statistical analysis in Rust significantly. The second excellent design of Rust is the consistent error handling, and especially without exceptions. We know that in C++, exception has been long a problem because it will introduce unpredictable control flow. This is critical for safety projects. And in our safety AUTOSAR adaptive products, to avoid this problem, we must disable the exception mechanism of C++. Instead, we introduced a result type to handle the function return value as well as the error codes. This result type mechanism was actually taken from the Rust. But Rust has other convenient syntax like the question mark. It can handle the error propagation conveniently. And third, the zero cost abstraction. Rust can support the system modeling with a very highly abstract and modular way, but it will not introduce runtime overhead after compilation. This makes it the truly scalable programming language, and it's very important for automotive software because we want to make our software that can both run on high-performance computer and on microcontroller with limited resources. And then the Rust is one of the few languages that can balance the complex system modeling and the low-level performance. And in addition, the type state pattern of Rust can help us to determine the resource usage at compile time so that you can avoid invalid state transition and avoid deadlock. And fourth, async. Rust provides a built-in asynchronous processing mechanism, async. We know that in our embedded controllers, embedded software of automotive ECU, we do a lot of I/O controls, just like networking driver and flash drivers. These I/O operations may be time-consuming, and we need to wait until some data are available or until operation is done. In C and C++, we need to implement this asynchronous processing state machine manually. But in Rust, we get this asynchronous processing mechanism for free. And then at last, cargo. Rust provides a built-in tool, very powerful, cargo. Cargo is not only a build system, but also a package management tool. In C and C++, if we want to introduce a third-party library, we need to do some configurations in CMake or Makefile. But in Cargo, you just need to add one line in the configuration file, and it will be done automatically. And Cargo can not only manage the libraries, the open source libraries from crates.io, but it can also manage the proprietary libraries in your company. Still, if you have some legacy codes in C and C++ and you want to integrate them into Rust, you still need Bazel or CMake on top of the Cargo. Okay, now let's move the perspective from from technical perspective to a more practical question. How much effort and how much cost can we save with Rust? As you know, Vector is a company with many years of experience developing AUTOSAR adaptive platform products and AUTOSAR classic platform with CNC++, so that we know exactly how much efforts and how much cost do we need at each stage of software development, so that we can estimate now roughly how much can we save, how much cost can we save with Rust compared to CNC++. First, for the implementation stage, we expect about 35% cost reduction, because Rust is a very expressive language, and the compiler of Rust can give very detailed and useful hints for the error. So the Rust is very close to, if it compiles, it works. Second, we know in CNC++ we need to do statistical analysis, but the compiler of Rust itself can already do very comprehensive checking rules for syntax errors. And Rust has also an own statistical analysis tool called Clippy. Clippy can also do very comprehensive checking rules, so that we can reduce the effort and the cost for statistical analysis with Rust significantly. And in CNC++, in addition to statistical analysis, we also need to do semantic analysis to avoid memory corruption problems. But in Rust, the safety, the memory safety is already guaranteed by the mechanism of Rust, so that we can remove this part of work completely. And then in code review, since Rust is much less complex than C++, we can also save some efforts in code review. And last, testing. In CNC++, for the testing, you need to introduce third-party testing framework like Google Test. And you need to do some configurations to set up the testing environment. But in Rust has a built-in test framework, so that you can write your unit test cases along with your code implementation. It's very convenient for usage. Now let's zoom out to a higher perspective to see the whole life cycle of the software product. Even though using Rust in the software development of automotive software can reduce the cost significantly for the whole life cycle. The reason is quite intuitive. If you make a software product with high quality and it is very expressive, you can automatically save the efforts for debugging, for after-sales support, and for maintenance. So that we estimate we can save cost in terms of development for the total software product lifecycle by about 20%. This number is also consistent with the experience of Google with Rust. And if you are interested in details, we also have an article. We also have an article in our website showing our insights about the ecosystem of Rust and the application in automotive system. We know that today, efficiency improvement and cost reduction has been a keyword for automotive industry. And we believe that Rust is a technology for the future to help us achieve this goal. But still, it needs some time. Now I will explain why it still needs some time for the Rust application in automotive applications. First, we need hardware architecture support. We know that in automotive microcontrollers, we have various of hardware architectures. Some are even proprietary, like the Infineon 3-core Oryx, like Renesas RHA50. And in recent years, the ARM architecture is on the rise. And in the future, maybe RISC-V architecture will become applied in automotive industry. So if we want to applied Rust language in the microcontroller, at first you will need the compiler support for this hardware architecture. And for safety projects, you even need a AZOD qualified Rust compiler. Now today, a high-tech company can already provide AZOD qualified Rust compiler for 3-core Oryx TC3, TC4, and for ARM architecture. But for Renesas Arch A50, there are still no Rust compiler available. But we believe this problem is solvable sooner or later. The second challenge is the code coverage. Rust has its own code coverage tool, LLVM Carve. LLVM Carve can already do very good statement coverage. But we know that in safety requirements with AZOD, only statement coverage is not enough. We will need 100% MCDC coverage for our codes. And since Rust introduced some new data structures, there are still no open source code coverage tool for Rust that can do MCDC coverage well. So we consider this is the biggest technical gap for the Rust application in automotive. But the good news is Vector has also our own code coverage tool, VectorCast. In this year, we are going to support Rust in our code coverage tool that can help you address this problem better. And third, the qualification of the Rust libraries. If you want to apply Rust for your production software of your automotive controller, you need at first the qualification of the standard library and the third-party libraries. And you will never need AZOD qualification. This will cost some effort, of course, but we believe that it's rather a matter of time. And at the end, metrics, this is not that urgent topic, but it's nevertheless very important. In safety critical systems, we want to control the complexity of our programs, so that we need metrics to measure the complexity of our software. In CNC++, we have established metrics like cyclomatic complexity, nesting depth, and we can give a clear number for the limits. But in Rust, since it introduces new structures, data structures, we don't have established metrics yet. But this is not critical at the moment, but we will solve it in the future. Okay, so much about the technical challenges and opportunities. Now let's look at the engineering perspective about how can we integrate Rust into AUTOSAR. As you already know, the Vector has already very mature AUTOSAR adaptive platform and AUTOSAR classic platform products. Both of them have already achieved AZOD qualification. They are developed in CNC++. So to rewrite these products with Rust completely is not economical and also unnecessary. A more practical approach is to develop safety-critical applications in Rust and then integrate them into the existing AUTOSAR adaptive platform and classic platform. Let's look at the AUTOSAR classic platform at first. The AUTOSAR classic platform is developed in C language. We have base software layer, and we have the RTE layer, and we have software component on top. So if we want to integrate a Rust software component on top of the RTE that are generated in C code, you need a Rust to C adapter. The Rust to C adaptation is quite straightforward because the C language has very stable ABI, that's the application binary interfaces, which are generated after compilation. There's no name mangling in the C compiler, so that the the ABI of C language is deterministic. You can match the Rust function directly to the C function. In addition, the C language has very simple data structure. You can map the C types simply to a Rust. And nowadays, there are already mature tooling like ByteGen, C-ByteGen, that can help you generate the adaptation layer, the Rust to C adaptation layer automatically. We also have a public article in our website that explain how can you use ByteGen to generate a Rust to C adapter and then integrate the Rust software component on top of the RTE step by step. But the issue is this approach relies on an open source tool, which is not qualified. And to address this problem, the latest version of our vector AutoSAR Classic platform can now support the generation of Rust API in our RTE, so that you can integrate your Rust software component directly into our RTE. This approach can better leverage the safety features of Rust. And then let's look at the AutoSAR adaptive platform. The situation is different because to integrate Rust into a C++ environment is much more complicated. The C++ language doesn't have a stable ABI because C++ supports function overloading, and to distinguish the different functions with different parameters, the C++ compiler will add symbols after compilation for the functions. And the different C++ compiler have also different name mangling rules, so that you can hardly match the Rust functions to a C++ function. In addition, C++ has complex data structures like classes, inheritance, templates, which you cannot find a direct mapping in Rust. And furthermore, the exceptions and RTTI, that's the runtime type identification mechanism of C++, is not available in Rust. And on the other hand, the ownership and lifetime model of Rust is not applicable in C++. So overall, it's very difficult to integrate the Rust application directly into a C++ environment. So we choose another approach. We develop a very lightweight C code-based intermediate layer on top of the C++ interface of adaptive platform. And then you can integrate the Rust application on top of this C-based intermediate layer with the approach we described in last slide. This approach is also recommended by the AutoSAR official application document. But of course, to write a C code-based intermediate layer on top of the C++ interface of adaptive platform will take some efforts, and it's not so simple. To address this, Vector has also provided a product called Application Framework. Application Framework is an abstraction layer between the applications and the actual middleware in production environment on high-performance computer. We know that when we develop applications on HPC, at the beginning, we may not know what is the actual production target environment. It may be AutoSAR adaptive middleware, or it may be other middleware like DDS. And we may also have a mix of applications. Some are developed in C code, C++ code, and some are generated from Simulink, and some are even written in Rust code. And we want to simplify this process of deploying the applications into the actual production environment on the actual middleware. So the application framework of Vector does abstraction of the middleware, and so that we can decouple the application development with the middleware. At the base, we provide the data model, we build a data model of different middleware, including AutoSAR Adaptive, and like DDS, and even the vector simulation kit. We also provide a code-based configuration tool. It's very lightweight, and you can easily integrate it into an AI-based development environment today. This configuration tool can also support the import of common data format like AutoSAR AR XML and Conversa VSS. Then you can do the configuration for your executables and interface of your applications, and then you can generate the codes for the abstraction layer, as well as the control module for the scheduling of the applications. Now, these interfaces to the applications are generated in C++ code by default, yeah. But you can also choose to generate it with C code so that you can integrate your Rust software, Rust application on top of this C interface with the approach we described in classic platform. So at the end, a short summary. In this presentation, we introduced a new programming language, Rust, for the automotive software development. And Rust is well known for its high efficiency and high reliability. We believe that Rust is a very high potential technology for the automotive software development. And AutoSAR is the best practice of the software standardization in this automotive industry. We believe that combining Rust with AutoSAR can help us build a reliable and scalable software for tomorrow's critical and distributed system in a more efficient and cheaper way. And we also introduced a solution to integrate the Rust applications into the existing AutoSAR adaptive platform and classic platform. Nevertheless, the application of Rust in automotive industry is still at an early stage. It has also challenges, but we believe that Rust is a high potential technology for the future, and we are glad to discuss with you about this topic later. Thank you.
Are there any questions you would like to ask? You have now the chance.
Good afternoon. Alessandro Sansonetti from ST Microelectronics. AutoSAR Classic and AutoSAR Adaptive are not finalized in terms of specification. We saw that, for example, there will be new concept, DMA hypervisor for the Classic and other. Are you planning really to design a new module inside the basic software using Rust? Or the basic software from Vector, the microsar, will not use any Rust coding for the new modules?
Okay, thank you. You are right. There are still new specifications for AutoSAR Classic and Adaptive, but to integrate, to develop this kernel, this base component in Rust will need adaptation with other existing base components. So it's rather much more effort than the approach we described here, that we only integrate the applications on top, because we have a very clear interface to applications in classic platform, that's RTE, and also in adaptive. So that's the approach we choose today. We are not intending to rewrite the basic components of the AutoSAR with Rust. at the moment.
Because, for example, for the hypervisor is very critical and could be really interesting to have Rust coding for at least a few of the new components that are in concept today in AutoSAR.
Yeah, that would be interesting. But as I said, there are still challenges, like we don't have the code coverage tool completely, and we don't have the compiler support for all the hardware architecture. So we believe that at the moment, for the current projects, we still need C and C++. Rust is rather for the future.
Thank you.
All right, thanks a lot. Are there any other questions? Oh, okay. We will start here.
Okay. So Rajat from Renaissance. So first I will, so for RH850, it also supports actually the Rust compiler for high tech.
Oh, okay, that's new for me. I didn't know it before.
Yeah,
Sorry, but thank you for the hint.
My question is, as you said that currently the use case is like to use the Rust for mostly at the application level at the top, and then we use the legacy code which we write in C, C++ for the layers below RTE. So which means we can right now go into some mass production development projects.
As I said, there are besides the compiler support, we still have some other challenges like code coverage and metrics. That's so. Yes, you can. Like I said, our Volvo has already using Rust in their production software, as the public information shows. So yeah, you can. There are already cases, but I'm not sure if other companies can go with it.
Okay, and the second question would be. So we have different modules in the AutoSAR stack. So does it make sense that we only do some critical modules like the crypto module or some safety related critical modules in Rust, and the rest of the modules still stay in C, and then we can integrate them together somehow in the basic software stack? Or we completely change the full basic software stack to Rust?
Technically, it can be done, just as the other gentleman asked, like in hypervisor, it can be done technically, but because of the project pressure and because the human resources problem, we don't intend to do it at the moment. Instead, actually, we are developing another brand new product with Rust, but I cannot tell you what it is now.
Thank you.
Thank you.
Yeah, so I think the Rust applications you mentioned in your speech is almost all in the application layer, right? But especially in AutoSAR CP or in the MCU application development, the industry are usually using model-based, using Simulink. So I think for Simulink generated code itself, I think it's already safety enough. So why we still need a Rust coded application?
I'm not sure if the generate, if you still, I believe you still need to do some statistical analysis and testing, unit testing for the generated code, right? Can you already trust the generated code completely?
Yeah, we could do some model in loop or back-to-back test with such like Simulink test to test the generated code.
Okay, if you already have a tooling that you can generate 100% safe codes, yeah, then you can, and it works now, I believe. So you don't need this Rust. But I rather talk about that you do a code-based development for the applications.
So that's more useful in adaptive
No, also in C, also in Classic, somebody do code-based development.
Okay, okay. Thank you.
All right, thanks a lot. Are there any other questions you would like to ask? If not, there's one other.
Hi, Rudi Dienstberg from Lauterbach. I actually have a question about the AutoSAR specification, because the AutoSAR specification, both in classic platform as well as in application, as well as in adaptive platform, based on C API and C++ API. There is a Rust work group in AutoSAR. Do you intend or participate in creating this API also as a Rust API?
As far as I know, we don't be part of it. We just pay attention how is it going, but we don't intend to introduce Rust API into the specification. As I said, we can already generate a Rust API in RTE.
Okay, thank you.
Yeah.
All right, thanks a lot. Any other questions? All right, then thanks a lot to you all. You now have a few minutes. You can maybe, if you would like, to go to the panel discussion in the ballroom. And afterwards, we're done. Thanks a lot.